Listeners of the video, if you are very much comfortable with the concepts of energy in water, like pressure energy, kinetic energy, and gravitational energy, concepts in energy, if you are very much comfortable, you can proceed to listen to this video. Or otherwise, it is better to listen to my earlier video I have uploaded in the YouTube, and its URL is provided here. The first step in design of drip irrigation systems is to know how much will be the discharge rate one would get from the outlet of a already installed pump in the field. It is very much obvious that if the velocity of flow at the outlet is more, then the distance of throw will also be more. X will also be more. So there is a relationship between velocity of flow and the distance of throw and also the height of the pipe, Y. So the relationship is something like this: V squared by 2G. It is the kinetic head of the jet of water at this place is equal to X squared by 4Y. So X is measurable and Y is also measurable in the field. So once we measure X and Y, we can substitute in this equation to get the velocity of flow. We know very well that discharge rate is velocity into cross-sectional area of flow. Cross-sectional area of flow can be very easily found out if you know the inside diameter of the flow passage here. So V into A, you will get discharge rate that would be obtained at the outlet of the pipe here. This is an approximate method only. If you want to measure the exact quantity of the discharge rate, it is better, if it is possible, collect the delivering water in a storage tank and note down the time, and note down also find out what is the volume filled, and volume divided by time. Volume divided by time, you will get the discharge rate. So this will be a better way of finding the discharge rate that would come out of the outlet of the pipe before drip irrigation system is connected. So it is a general tendency that people who are new to drip irrigation design, who would normally make use of this discharge for design of drip irrigation systems, but it should not be done so. If we connect a drip irrigation system at this point, we are going to load the system and we will not be able to get same discharge, and we will be getting only less discharge than this discharge. And how much discharge we will get if we connect the drip irrigation system has to be found out, and that should be used for drip design. So let us see now how we can find out how much discharge we will get if we connect the drip irrigation system with the existing pump and pipe. So for that, we make use of the equation that pump power before drip connection and pump power after drip connection are same, but really pump, this is outlet, this is the output power of the pump. Output power of the pump before connection and output power of the pump after drip connection will be slightly different, but to get a kind of an approximate result, we assume that both are equal, and we make up an equation, and from that equation we find out what is the corrected discharge when drip irrigation system would be connected. So it is Q. We have already seen in our earlier video that the pump power is Q into H into 10. Q into H into 10, and on this side also Q into H into 10, and this 10 gets cancelled, and we get Q1. Q1 is the discharge rate before drip connection, and this all these terms put together are it is total head that is developed before drip connection. Total head comprises of static lift, and also the losses of pressure head when water passes through the pipe, and also when water enters into the pump through the foot wall, there will be some loss. So all these losses, this loss and this loss, all are put together, and that loss is taken to be 5% of static lift, 5% of 26 meters. It is conventional to take 5 to 15%, but conservatively we can take 5% of static lift to be head loss, this HL, and V squared by 2G is kinetic head. So normally in these kind of calculations, V squared by 2G will be negligible, and it has already been proved that V squared by 2G will be very, very less. So we neglect V squared by 2G here. And pump power after drip connection also has same set of variables. Q2 is the discharge rate when drip system is connected, and HS and HL are same, static lift and head loss in the pipe and foot wall. Along with that, we have added one more term called pressure head needed for drip system operation. Pressure head needed for drip system operation, minimum we need 10 meters. That's what the government of India recommends, that you need to have at least 10 meters pressure at the outlet. But if drip irrigation system has to function well, at least 15 to 17 meter pressure if we have it, our system will work very well. So let us take a data in which HS is 26 meters, HL is 5% of 26 is 1.3 meters, and V squared by 2G we will assume it as 0, and Q2 again HS is 26 meters, HL is 1.3, and we will take a minimum of 10 meters. So if we substitute with data for all the variables, we will get Q2 to be 1.46 liters per second. This is less than 2 liters per second. What does this mean? This 1.46 liters will be the discharge rate. Most probably we will get after drip system is connected, if our operating pressure at this place is 10 meters of pressure head. But this calculation, from this calculation, we are able to find out what will be the reduced discharge. In this calculation, we also assume that this pump itself will be able to provide the additional pressure for drip system connection. But we may not know really in the field the pump will be able to deliver additional pressure we need. So that can be found out in the field itself. That can be found out in the field itself. How can we find whether the pump is able to produce this additional pressure at all? So for that, the equation we use is this thing: total head upstream of valve at this place, total head upstream of valve is equal to total head downstream of the valve. It means that the energy before energy upstream of valve and energy upstream of energy downstream of valve are same. It means that energy can neither be created nor be destroyed. So whatever energy loss coming in between, happening in between, is also have to be accounted. So total head upstream of valve is equal to total head downstream of valve plus loss in the valve. So total head downstream of valve is V squared by 2G only, because the outcoming water has only kinetic head. It does not have any pressure head. And we also neglect gravitational head because we can take the datum to be at this level. So in that case, the gravitational energy before upstream of the valve and also downstream of the valve, both will be same. So we don't need to account gravitational energy in this case. And loss in valve can be approximated to be 0.5 V squared by 2G. It's approximate only. So we get total head upstream of valve to be V squared by 2G plus 0.5 V squared by 2G. We get 1.5 V squared by 2G. So we take a small numerical example, like we will take H to be, 10 meters. So we want 10 meters to be developed at this place, and X to be Y to be 1 meter. The height of the pipe from the ground is 1 meter. In that case, if we substitute, we will get X to be 5.16 meters. What does this number indicate to us? If the total head developed upstream of the control valve here is 10 meters, we will get a throw distance from the jet to be 5.16 meter. The jet will be thrown to a distance of 5.16 meters. So only if you are able to get a throw distance of 5.16 meters, we will be able to get a pressure head of 10 meters upstream of head. So how can we make use of this data in the field to test whether the pump will be able to deliver 10 meter additional pressure head? So what we should do is we should close the valve gradually. As you close the valve gradually, the jet issued will be thrown to a larger distance, something like this. And if you are able to get a distance of throw to be 5.16 meters, or approximately at least 5 or 4.5 meters, we can understand that the pressure head that has got developed at the upstream of the valve is 10 meters. The best method for assessing pump capacity is to have a set of pressure gauge, a flow meter, and regulating valve. So if we have this kind of a system, we will be able to get correct results and exact results. But only thing is that carrying all these accessories for every field is difficult. But if you are able to take with you this setup, always it is better. You will get a better data when we connect this setup with the outlet pipe, and this is a pump, this is a well. You can control the regulating valve and increase the pressure at this place to be 10 meters or 15 meters or any design pressure you want. And you can find out what is the flow that is happening here, that is going here. And for that discharge, you can proceed the design of a drip irrigation system. And it also helps you know whether this pump is able to deliver a pressure head of 10 meters at this place. So this is the best method of assessing the pump capacity.